All right, so the last few weeks we've been talking about vision, right? We've talked about all kinds of aspects of vision. We talked about color vision, we talked about depth perception, we talked about spatial vision, we talked about shape and object recognition, right? We talked about a lot of things. The only thing we haven't talked about yet is stuff that moves, right? Which is fairly important. I don't know if you guys have ever noticed. Even we should think about not just about things that move toward us or away from us, around us, right, Skylar, in our visual world, but there are also those things that are stationary that still move relative to you, right, as you move through the world, right? So all of you move from time to time, and even stationary objects will move through your visual field, right, even if they're not moving on their own. So there's two kinds of visual motion there. We'll think about those, and it'll be exciting. All right, here's some learning objectives. We can skip that. All right, so if we want to detect movement, right, what's the simplest, easiest way to do this? If we wanted to set up a detector in our visual system to go, okay, something's moving, right? How do we know if something is moving? At one time point, it was in one location, and at another time point, it's in a different location, right? It's that simple. That's motion. Okay? If something is in one location and 10 minutes later it's in the same location, has that object moved? No. Not as far as our visual system can determine, right? Maybe while you turned away, someone moved it and moved it back, but we don't care, right? It's got to be there, and we've got to detect that motion. So one of the ways that we can do this, it's actually pretty interesting, is using something. This is really basic. It's called a Riker detector. Okay. This bar is the object, and that object is going to move in space, right? And as it moves across your visual field, you have two different receptive fields. Receptive field 1, this is receptive field 2. Okay? It's pretty simple, right? When the bar moves across the first receptive field, it gets activated. Put a green check mark there, that's going to be awesome. And that's going to send a signal. Doesn't show up very well, does it? It's going to send a signal down that axon, right? When the bar gets to location 2, the second detector will get active, right? Okay. Second receptive field, and it will also send a signal. Now, one thing you may have noticed here is that the path for signal from cell 1 is longer than the path of the signal from cell 2, right? So for those of you that aren't aware of this, it takes longer to travel a longer distance, assuming we're all traveling at the same speed, right? Because we're all traveling at the speed of a nerve impulse here. It's going to take us longer to travel that extra distance than it does the shorter distance, right? So we're starting one, but it's got longer to travel, and then we're starting the second one, right? Okay, that's going to be more direct. So what happens? Why? So we can detect vision. That's why. So what happens is when that first signal makes it to this, it's called a comparator, makes it to this spot right here, right? If it arrives at the same time as the signal from location 2, right, we get a bonus, okay? They both work together and they give you a bigger response to send forward, and you go, okay, something was definitely moving. Because both of those signals arrived at the same time. How could they arrive at the same time if that object was moving and it started at 2 different times? Because the first one took longer, right? So let's imagine we were all going to go over to the Student Center. That sounds like a blast, right? We're going to go out, we're going to go to the Student Center. Half of you, though, instead of going to the Student Center directly, I'm going to need to send you over to Fat Patty's to pick us up something to eat, right? Okay, so that's a longer path, right? So I send you first. The people picking up food, you send them first. We wait a while, the second group goes. If we both arrive at the same time at the Student Center, then that's going to be perfect timing, right? Okay, that's what's happening here. Both of those are arriving at the same time, so we know motion is moving and we know which direction it's moving, right? So that's great. If that bar, Charlotte, moves in the other direction and it activates this cell first, what happens? Whoa, there's no delay, right? It's impossible. If I started those of you who are going directly to the Student Center before I send the rest of you to Fat Patty's, that all of us will get to the Student Center at the same time, right? Because those going directly to the Student Center are going to get there first. It's so much faster, it's the direct route, right? And so then when the other group finally gets there, you guys have already gotten bored and you decided to get a burrito, okay? You're like, well, I'm not waiting on that. So then, if it's going in the other direction, this particular unit would not detect that motion. And so I know some of you are really worried, like, how do I know stuff's moving in the other direction? You've got a whole other set of detectors, right? So you've got, let's just imagine an infinite number of these, okay, for all directions and different speeds, right? So you can detect motion going in different ways. Does that make sense? Awesome. Now, some of you have seen this before, right? How many of you remember that Hubel and Wiesel video that we watched? Did we watch that in this class?
No, we didn't talk about that.
We did talk about this,
Yeah.
right? We didn't watch the Hubel and Wiesel video, really?
No.
Wow.
And that's a good video.
Yeah, it's a good video. You guys should watch it. Just play it on loop at your house. These guys won a Nobel Prize from recording electrical signals from the striate cortex of a cat. These are from cat and monkey. You can do it in people too. Chandler, a lot of folks won't let you drill in their heads, but that's okay. Go
I
ahead.
was going to interrupt you, I'm sorry. So how do we detect movement, or how would that pathway look if it was coming straight at us?
Yeah, so that's a brilliant question. And actually there are, they're like edge detectors, right? And so the edges of something as they're moving to you,
It goes in and out of this?
and it's actually moving in all directions, and so you can accumulate. So this is one, right? And you have, remember, an infinite number of these, but you can combine these in almost an infinite number of ways too, and so you can pool all that information. That's really actually a good question, because what are they going to do for the lab today? They're going to be looking at not just component motion, but this complex kind of global motion as well. And that's sort of what you're asking about. We'll get to that in a few minutes. You're really worried about things coming directly at your face?
Don't want to get hit.
Don't want to get hit, right? No, that's perfect. So here's the basic idea. If we have a bar and we move that bar in different directions, there is a set of cells that's going to get really excited when that bar moves, in this case, kind of up and to the right just a little bit. Not so excited when it moves in other directions, right? These are actually drawings that were made from recordings from actual brain cells, right? So they'll isolate one single brain cell, typically in the striate cortex and V1, visual cortex, primary visual cortex, all the same thing. And they will move that bar around, right? Just a single bar. And you guys are going to move a bar later, and we'll kind of see how that works in the lab activity. It's going to be exciting. Did you guys bring the electrodes? Oh, they forgot the electrodes. We'll get the electrodes and the drills later, so you guys will be fine.
Drills.
Yeah, drills. So, what will happen is that bar will move and it will excite a cell, and that cell will be active. You have many cells tuned to all of these different orientations, right? Not a big deal. So how many of you are familiar with the motion after effect? Yeah, so basically this is, sometimes it's known as the waterfall illusion. I know you guys spend a lot of time staring at waterfalls, right? Seems like a good pastime. If you had other pastimes like reading books, Alex, you'd probably do better at trivia, but staring at waterfalls will at least give you a good example.
You just saw me, Alex?
I did, Kyle. I told you I would do that. For whatever reason, I've got Alex and Kyle in the same category. So, the motion after effect. If you stare at something that's moving in a particular direction for an extended period of time, and then you look at everything else, stuff will move in the other direction, right? Unfortunately, this particular video is not playing. But that's not what I wanted. All right, let's find the one here that's the motion after effect. I think it's this one. So this is a great website. We'll spend some time on this website today and also in a couple weeks, right? This is called the spiral after effect, or it's basically the same idea. What you do is you just sort of stare at the center of this for an extended period of time, right? Okay. And then you just want to look at something else. If you stare at it for 20 or 30 seconds, and then look at other objects. Let's see if we can get the lights out. I think, is there a glare for some people? Is that helpful? Just continue to stare. stare at it, 20 or 30 minutes.
Minutes.
Seconds.
Oh.
Yeah, it's crazy, isn't it? Yeah, when it works, it's very powerful, actually. Has everybody experienced it?
No.
You may need to move to one side or the other to get perpendicular to the screen.
So what am I supposed to be experiencing after staring at it?
So if you stare at it, you fixate in the center there, Alex, and then you look away, what you'll see is the other, whatever you look at should appear to move a little bit.
Ooh, ooh.
Yep, there you go.
I'm seeing a star, like a burst.
That's probably close enough. Okay. So this is called the motion after effect. The reason they call it the waterfall illusion is the first person to describe it. He did spend a lot of time staring at waterfalls. And after he stared at the waterfall falling down for a long time, he would look at the trees, and the trees all looked like they were rockets going up into the sky, right? Because you were seeing things move in the opposite direction. Now, it's a little difficult with that spiral because so much is moving in different directions. But if we were looking, Mary, at something going in one direction, and then we looked away, what we would see is something going in the opposite direction. Now, how many of you remember that time we stared at the apple, right? And then we looked away from the apple and we saw the inverted colors, right? And that was because when we were staring at the green apple and the red leaf, it fatigued the green and the red. And then when we looked away, what came through most strongly, even though there wasn't any excitation above and beyond baseline, what came through above the sort of fatigued red cells or fatigued green cells was just that red activity, right? So the apple appeared red because baseline activity is better than suppressed activity, right? The same idea is going on here with the motion after effect. If you look at something and it's rotating clockwise, right, then all of your detectors for clockwise motion will get fatigued at some point. And when you look away, even if something's not moving, those anti-clockwise or counterclockwise motion detectors will be active at baseline, right? Just a little bit, just because they're ready there to fire action potentials, and it'll appear as though things are moving in the other direction. Does that make sense to everybody? All right, motion after effect, that's a good one. Okay. And here it is in this fun graphic form with these great little characterized neurons here, right? Basically, if there's no motion, nobody's pulling one direction or the other. If you're looking at rightward motion, all of your rightward motion detectors are getting excited and they're really expending a lot of energy. They eventually become super tired. I don't know if you guys have ever been in a tug of war, but that's what happens. And then these guys over here are like, awesome, we're not doing anything, but it looks like we're pulling in this direction a little bit. So you're going to have a little bit of that perception that things are moving in the opposite direction.
So that's after the rightward motion.
Yes, after you've stared at the rightward motion for some period of time. And it works with any direction.
So this is why you see, like, why after looking at something that's moving in one direction, you're going to see it in the opposite direction when you look away.
It's going to appear to move in the opposite direction. Yeah. Because those detectors for the opposite direction motion have not been fatigued, right?
Right.
The ones for the actual stimulus you've been staring at for some period of time, they're obviously tired, right? Because you've been staring at that motion for some period of time. Does that make sense? So it's kind of like when you go to trivia, Kyle, and you beat a team, but the team you beat's not very good, so it looks like you beat someone, but in reality, you were just kind of there at random chance.
Take what I can get.
I didn't know you were going to come with so many great examples for us. We appreciate it.
Try to help.
I know. You're doing your best. Thanks. All right. Now, I know, right? Who's ready to move their eyes? There's different kinds of motion. There's object motion and observer motion. This is what I was talking about earlier, right? Sometimes you're stationary, right? And for example, here the car moves, right? The car moves from one location to another, and that's going to change the placement of that image on your retina, right? And so any of those motion detectors are going to determine that that's motion, right? So that's going to be great. Okay. However, there's another situation, right, where you can actually turn your eyes, right? You can actually move your eyes, and that still moves an object on your retina, right? And so in this case, you were looking at a car, but you're rotating your eye, you know, in one direction or another, okay? And that's going to change the position of that car on your retina as well, right? What's really exciting about this, so how do we know the difference, right? So you're thinking, well, how do we know if I'm moving my head or if I'm, you know, moving my head or eyes, or if the object itself is actually moving, right? And kind of the first obvious answer is the correct answer. Well, you know if you're moving your head, right? But how do you know if you're moving your head and eyes, right? So there's actually output. Anytime you send a motor command to move your eyes, there's a copy of that information that goes back into your visual system so that you understand that you're moving your eyes. Now, there are a couple ways to trick that, which are kind of fun things that you can do. One is you can close one eye and then like poke yourself in the side of your eye. So if everybody wants, I know, just go ahead and do it. Go ahead. It's a lot of fun. Close one eye and just close one eye and just poke yourself like on the eye and watch what happens to the visual image. It's really, go ahead, Laura. It's not going to cause a problem.
What?
Close one eye. There you go.
I don't like that, makes my eyes water.
Yeah. It's weird, isn't it? So when you do that, what you see is the image seems to kind of shake and move around itself, right? Because you're not actually sending that motor copy. Now, if you close one eye and you start just like moving your other eye around, you kind of have a normal experience, right? It's not an abnormal situation because you're getting that copy of that information. Oh, I'm moving my eye around, so I don't need to think that the whole visual world is shaking, right? But if you're not moving your eye and that image kind of shifts on your retina, right, and moves around, you get a completely different perception. That's pretty cool, right? There you go. Just go around poking your eye all the time. Try it while you're walking down the street. It's really challenging. All right, so what do we do? How do we know? Again, what are the fancy things that we do to know that the object's moving and not me, or I'm moving through the object? The first is something that we were just sort of actually looking at called saccadic suppression, right? We talked about saccades before, right? Those rapid eye movements. When you move your eyes around, you don't get blur, right? You would imagine if you were just, you know, spinning your whole body around, right? So if you do that, just kind of spin your whole body, not your head. If you spin your head, it sort of does the same thing, right? It's kind of hard to bypass that vestibulo-ocular reflex. But if you rotate your whole torso around, you will see things blur, right? Okay, so you get some blur. If you just move your eyes around, that blur disappears, right? Even if you're moving at the same speed and in the same kind of plane, because of this concept of saccadic suppression. So your brain knows, again, because you're sending that motor command, hey, I'm getting ready to move my eyes really fast, okay? The world is not moving, I'm not moving, I'm just moving my eyes. Let's suppress anything that happens between point A and point B so I don't have that blur in between, right, Emily? Because that can get really confusing, okay? And that's, again, all related to these eye movement commands. Secondly, we look for large-scale motion, right? Okay. And optic flow. So we want to look at, is there just a small piece in my visual world that's moving, right? Okay. Or are there larger chunks that are moving as well, right? If everything seems to be moving, then that's probably not the object, that's probably me, right? Assuming we're not in the middle of an earthquake, if you're walking down the street and a building appears to move across your retina, that's probably because you're moving relative to the building, right? Okay. And that's also part of optic flow. If you guys walk down the street, city street has a lot of tall buildings. If you walk down a corridor like we have here in Harris Hall, what you will see is things will start to expand and move past you, right? And so you have that optic flow. And if you're experiencing optic flow, so movement in your entire visual field, except for maybe you might argue that one little point in the middle might not have a lot of movement there, right? But if you're experiencing that movement and that change in movement as you're going through your optic flow, then you know I'm moving relative to the objects. Chandler?
When you're moving like very fast with a lot of force in your body, or like a lot of shaking or vibration like on a roller coaster or something, did your brain, like in your eyes, try and compensate for that movement, or do they just kind of back off and like say this is too much?
That's actually a really good question. So what I would recommend if I thought it was safe for you to go to Camden Park and just ride a roller coaster 10 times. But I think if you get by once safely on a roller coaster there, then you're really doing something. Don't tempt fate for that second time around.
Do you not like roller coasters?
I don't like ones that my great grandmother rode. That's what that's fair, right?
Pretty sure they just take off broken wood and replace it with new wood.
Yeah.
They don't just like tear down the whole thing and rebuild it.
No, I think you're right. And I don't know who inspects that.
There's a lot of shingles on it. The shingles concern me a lot.
The shingles?
There's shingles on like the top of it. I don't know why. They just put shingles. I'm guessing it's to prevent from like rain maybe getting in the wood.
Oh, yeah. Yeah, you know, I don't know. I didn't design that roller coaster.
Then again, that owner has prevented that place from changing so much already.
Yeah.
So
So there you go. So this is like a real interesting problem, Chandler. And this became a real problem. It wasn't too much of a problem until probably, I'd say a few hundred years ago, right? A few hundred years ago, the fastest you could move was however fast your legs would carry you, right? Okay? Which is what?
Very good point, yeah.
Right. So the fastest you could move through the world was that speed, right? Whatever that. I mean, what's the top speed of someone who can run in a sprint?
Usain Bolt.
Yeah. I mean, that's even we can even use that as an extreme
30,
example.
40.
Yeah, right. Let's say 35 miles an hour might have been your top speed for a brief period of time, right?
Yeah.
More likely, it's going to be in the 20s. For your average everyday person, you know, like 2. So you're moving through the world, right? And that's as fast as you can go. Chandler, you're checking that out, right?
Yeah, I was looking up top speed.
Yeah. What was it?
28.
28.
20 miles per hour.
Yeah, 28 miles per hour, right? So let's round up to 30, just in case you're going downhill with a little bit of wind behind you, right? So let's assume 30 is your top speed as a human with no assistance, right? Then we started doing something else. We started riding on the
steroids.
Okay, well, I was going to like not skip that far ahead, because I think even with steroids, like 30's your top, right? I was thinking we started riding on the backs of things that were faster than us, right? Like horses. Like, what's the top speed for a horse?
A lot faster than me.
Yeah.
50?
60?
Yeah, 50, 60, I don't know. That's a reasonable guess, right? So we started riding on things. Then we thought, well, horses aren't fast enough. Let's see if we can make something even faster than a horse. And so we came up with cars. Those were pretty fast, and trains and so forth. And then, where things got really carried away, airplanes.
Yeah.
And there was a guy, Herschel Leibowitz, a few decades ago. He was a big visual psychophysicist, so he tested visual perception, and this was his deal. But he spent the vast majority of his career working in the field of aviation, right? So he was kind of coming on in the 30s and 40s, 50s and 60s is when he was really doing a lot of his work. And so that was a burgeoning field at that time, right? Because planes were just getting to the point where they were going really fast, and there were a number of them in the air. And he was the guy who would calculate, like, how far away do you need to be able to detect another plane to make sure everybody has time to adjust, right? Because there's a certain point where if you're so close, there's no way that you're going to be able to make a decision to change your course, right? And a collision is going to be imminent. And the same thing is true with a car, right? There's a certain point where you're close enough to another vehicle that you're not going to be able to get that visual information in, processed, and out as a motor command fast enough to avoid a collision. So you should drive safely, right? I think about this a lot while I'm driving, especially on the interstate. I'm like, you know, I'm right now doing something that I'm not evolutionarily prepared for. And that's driving at 80, 85, 95 miles an hour, whatever that is. I'm not prepared for that, evolutionarily speaking, right? I'm prepared to drive my car about 30 to 35 miles an hour. That's about where we are as a species, right? And how many of you do that?
Like no one.
Yeah, you only drive 35 and a 15, right? 35 and a 15, right? I know how you guys drive. I see some of you on the road, briefly as a blur. So I think, Chandler, that's a great question. It's a great line of thinking.
I guess it would, yeah.
I would.
Alright, just one more question, like that force with having all your blood and circulatory system affected by things like that, change the way your brain would want to operate. That, like, I guess that's a lengthy, pointless question, but.
Well, I don't know if it's pointless, but Lengthy, probably.
Yeah.
Yeah, so blood flow makes a big difference as well. This is a real problem. This is why they put pilots in G-suits. Are you
Yeah.
guys familiar with G-suits? So they're like pressurized suits to make sure you maintain enough blood flow to your brain so you don't pass out.
That's important.
That is important. And it wasn't so important back in like the Red Baron days, right? When again, your plane was probably just going fast enough to not fall. Right? We weren't really, but then, Dr. Atkins, what was this guy's name? And I tell them I think I'm contractually obligated to mention his name. He broke the speed of sound. Chuck Yeager, right? And so that guy came along, and then it's like, geez, people can pass out. Not that he passed out, but going at a high speed, making those turns, right? Because you might experience in a turn in a fighter plane, you know, several times normal gravity, right? And that's going to have a major effect on blood flow. And if you don't kind of have that stuff keeping you pressurized, you'll start to black out.
And I guess as well, like, if you experience like a mild form of that, like downhill mountain biking or something, you might feel a little bit lightheaded.
Yeah, same thing could happen. There you go.
What's large scale motion again?
Large scale motion, we're sort of looking at the entire visual field, right? So we're seeing that like lots of stuff and everything is moving, right? Not just like one little piece, right?
Peripheral and like everything.
Yeah, so like small scale motion or local motion is like a tennis match, right? So if you watch a tennis match, there are only three things moving during a tennis match, right? Player A, player B, and the ball, right? That's it. And so just those things are moving, right? Okay, so you're not really too worried about it. Large scale motion is going to be, again, maybe you're driving down the road, there's, you know, entire hillsides are moving, right? Things like that. So it's just going to be a sort of a different experience. Does that make sense?
Yeah.
All right, now we've got two other sort of types of movement. One's called real movement and the other's called apparent movement, right? Real movement is just normal, continuous change in position in a natural image. What we mean by that is you're just looking out in the world and stuff is actually moving, okay? Not a big deal. Apparent movement, right, is change in position that is perceived from a series of static images, right? How many of you have ever watched a movie? Right there is apparent motion, okay? That's all it is if you've seen, of course now they're digital, but it's the same story. But if you've seen the old film, right, makes me feel really old to say old film, since, you know, just like 5 years ago things were on film. But I think now they're mostly digital. So when you pull the film out and you see it's just a series of images, one slightly different than the other. How many of you have ever made a flip book? Right, where you draw the little stick figure and he dances around, right? Because that's apparent motion due to a change in these static views. Your computer runs on this sort of apparent motion. Christmas lights. How many of you love Christmas lights that look like they chase each other, right? Those chasing lights. That's just apparent motion, right? It's a static image and it's just changing from time to time, and you think that that's motion. The marquee at the Keith Albee does that, right? Kind of has those chasing lights. You guys have seen that.
Still go to the Keith Albee. I mean, you brought it on yourself with the whole, you know, it makes me feel really old.
Yes.
Is that a valid thing? There's like shows that are like.
That's what I thought. I thought that was a bad joke. That's what took me so long to respond. I was going to let you have it, Mason. All right, so these aren't going to work, but you can check Michael Bach's website, right? And really, any of these things are going to be apparent motion, right? Because it's just static changes. This is actually.
Those eyes following your mouse.
I know, that's a ridiculous 1990s website gag, right? But this is one of my favorite.
They're so cute.
I know, right? But they appear to be sort of waddling, and they're not. So you can actually. I know, right? That's all they're doing, and then you put that on top of it, right?
They're like.
That is pretty cool, right?
Why does that happen?
Yeah. So, yeah, like the lenticular discs.
And like
Yeah, you're preventing some information on those black bars, right? So you're like preventing some information from getting there, so it looks like it's being hidden, and then it kind of pops out, right? Is what it's doing. So it's really kind of tricking your visual system, taking into account that that apparent motion, right? Because you're getting some apparent back and forth motion created from this overlying grid. You can slow it down a little. It's pigeons and worms. You can apparently
Oh, they're worms?
just do
I
worms.
thought they were just walking on the road.
You thought they were what?
I thought it was a road, you know?
Thought it was
like
a
they're
road?
walking on the
Oh.
road.
No, it's pigeons and
Duck
worms.
crossing. I can change the color.
Yeah, you can change that.
Ooh.
I know, it's exciting, right?
Yeah, this is like fun.
Yeah.
Let's do that.
In a couple of weeks, we'll actually spend a lot of time on this guy's website.
I love that it's called pigeon neck illusion.
Yes, the pigeon neck illusion.
Love that. Love that.
It must be exhausting. I'm doing this all the time.
So, that's all exciting, right? Awesome. If we flash things fast enough from one location to another, it'll look like the thing is moving. That's wonderful, right, Caitlin? But what's actually happening in your brain, right? Because that's what's really exciting. Like, how can we stick this into something squishy, right? Something biological.
Right.
So, there were some folks who did some measurements a few years ago, and what they did is they had basically two flashing dots, and they would have you kind of dial in the delay, right, between these dots, like how fast they were flashing, okay? And what they would do is they would say, well, okay, anything down here, you're not experiencing motion, you are experiencing motion, and anything up here is when you would experience motion. And they plotted this, and that's what we have here in this black line, right? So what we have is that is the line of where you experienced, where that transition was, when you were just able to say, yes, that is no longer motion, or yes, it is motion. You were right there at that threshold, right? That's the dividing line between the two. What's really interesting is when they measured activity from brain cells, they looked at, first place you're going to look is primary visual cortex, right? You think, okay, primary visual cortex, very important for visual information, right? So we're just going to do that. The problem is the responses of primary visual cortex did not match that threshold very well at all. However, there is a brain region called MT, now that stands for middle temporal area. Another thing you can use to kind of remember this is MT is motion, right? So it is the motion detecting brain region in your cortex, right? In visual cortex. And what you have is, if you notice the response properties of the cells in MT, they actually very closely mimic that perceptual threshold from humans, right? So it's kind of exciting that we have this brain region whose activity maps onto our perceptual capabilities. And that's always nice when you're able to tie the two of those together, right? Anytime you have something that is a perceptual capability, and you're not able to map that onto some neurological construct, then you have to think, okay, well, what's really going on here? What else is happening, and how can I make this fit, right? Now, we get into some problems, because not everything is perfect with your visual system, right? And one of the biggest problems we have is called the aperture problem, and we're going to spend some time in lab today going through the aperture problem, right? Now, Chandler, this really gets at the heart of the question you asked at the beginning of the class, right? If something's coming at you, how do I know what's going on? The problem is, this is complicated because you're only sampling small bits all over the place, right? And most of these bits are circular, okay? And the problem is, with that circular bit, right? If something extends beyond the size of your receptive field, right? Because your receptive field is kind of small. If something extends beyond the size of that receptive field, if it's moving, you can't see those ends. That single receptive field can't see that, right? And so what happens is when that object moves through, if it's moving through, for example, at an angle, let's imagine this square is moving down in this direction, right? if we only look at this black circle, what's inside of that, all we would see is the edge moving in that direction, right? Because we can't see either end of this to see that that end is also moving up and down, right? We can only see that edge as it moves back and forth through the aperture. Okay, does that make sense to everybody?
Can you read?
Not really.
Yeah, I can.
Does it mean, like, is it basically like you can't see stuff out of your visual field?
Right. So,
I mean, I'm sure it's.
Marissa, where's the breathing square? Isn't that the great one for this?
Yeah, I thought so. I thought it was on. You passed it.
Breathing square
It's
is
right
there.
there. Under.
Here?
Yeah,
No,
go down a
stop.
second.
Holy, there
Right
you go.
I found it. I knew where it was. So, if you look at this, this sort of highlights the aperture problem a little bit, right? So if you were to take a look at this, it looked as though that center square at first was kind of doing this number, right? Kind of expanding. But as you can see, all it's doing is rotating. Because you're only getting a small sampling of one edge, right? You're not getting the entire object, okay? And when you're only getting that small sample, that aperture, right? Which is like coming from a camera. See? It does, doesn't it, Chloe? It looks like it's,
Yeah.
but it's not. It's not at all. It's the exact same square. And you can, if you don't believe me, because I know some of you don't, what we can do is we can actually adjust the transparency. And then, of course, the illusion disappears at that point. But you can see I wasn't lying to you this time.
This
This time.
And so we have to imagine that in not such a flat way, right?
Yeah,
So
so-
that it's globular, it's layered, it's like.
Right,
That's a lot
absolutely.
more, yeah.
And you're only getting, so what you have to take from this is how do we solve this problem? Well, what we've done here is we've designed a way to really trick you, right? And we're not giving you any additional information. Now, in the real world, what you typically have is hopefully additional information. Right? Let's imagine a baseball's flying at your face, right? And you're sampling only from little bits of the world, but all of those samples you're going to put together, right? You're going to collect all of that information, and because you have bits from everywhere, you're going to be able to think about how that's expanding in your visual space. Okay? But that can be complicated by other factors, right? Okay.
Lack of depth perception.
Yeah, like if you were a one-eyed baseball player,
Yeah.
that could be complicated.
Reaction.
Reaction time. There are other things, and this is something we talked about a couple weeks ago. We talked about the contrast, spatial frequency, sensitivity, remember? I always think about this because how many of you are familiar with home field advantage? Now, what color uniform do baseball players wear when they play at home?
White.
What color is a baseball?
White.
If you're wanting to hide a baseball from somebody, especially if you're a pitcher, you try to make yourself, I mean, I'm thinking I'm going to wear like a big flappy jersey that's white, and then the ball's going to spend more time hidden by my body, right? So you're not going to be able to pick out that contrast. That's a thinker right there, right?
Now I'm gonna go to baseball.
I played softball, travel softball growing up, and a lot of the summer ball leagues would try and get like the neon jerseys, and they banned them from because you really couldn't see
Can't
them
see the
coming
ball.
like at all.
Can't see the
So
ball.
they banned like that color from being on a uniform and girls.
I can just imagine like at least a 5-game win advantage if Marshall would change their school colors from Kelly green to neon green.
Oh.
Yeah,
It'd be worth it, right?
No.
that'd be disgusting.
Fantastic, that's for sure.
I don't know. You guys think about these things. I think about it sometimes. So there you go. So maybe you should, like, if you're ever running a baseball team, because I think, Eli, that's a career for you, right? General manager of a Major League Baseball club.
Manager, yes, no.
Not the player,
Yeah.
general manager. You don't have to. You get to stand up in the skybox, you get to eat hot dogs, and you get to watch baseball all the time.
Oh, yeah.
That's the ideal job, not playing the game.
Yeah.
Right? You can get injured, people yell at you. Most of the time,
Expectation.
I know, most of the time people don't know what the general manager looks like. He's always just up there in a suit, just eating a hot dog. Or 2 hot dogs because he makes a lot of money.
Not
Because
the
he makes a lot of money. One of those beer hats.
Yeah, one of those beer hats. I don't think our team's going to be any good.
That's why I need the beer hat.
But you should think about, testing the contrast sensitivity function of your players, right? To see if they're going to be good at picking out that baseball on a bland background. People don't think about that, right? What will they do? If you sign a real, like, let's say you have a team that has 2 power-hitting lefties, and you're going to build a baseball park, what do you do? Guess what? You move the fence in as far as you can, right, for those pull hitters so they can hit more home runs. That's how you design your ballpark. But let's say you've got a guy who's got like a little trouble with contrast. I'll see people out there making like different colored padding on the fences so you can see the ball. They should, right?
But the padding's like green. It's not like
Sometimes
white.
it's green.
Yeah, but most of the time it's like a darker color.
Yeah.
They're not out there making
Just go with
it.
my example, Olivia.
Okay. All right.
I don't think they do it consciously. I think they
Yeah.
just make it green because
Yeah.
someone made it green.
Listen, I'll make it rainbow, I'll make it as gay as I can.
I think, then I wonder about like if there are too many colors and they're moving their eyes fast, like seizures.
That's what we want.
That's what we want.
Here's the other team, we'll make sure none of the people in our team.
We'll have it rotate, you know,
Yeah.
when it's our team at bat, we'll just
Yeah.
flip it up to green and then go back.
Yeah.
Makes perfect sense.
Just paint the padding as whatever's behind the actual padding. Like, if there are buildings in the background, paint them exactly like this.
Yeah, wow.
This is your class, I hope you know that.
I know.
You chose this.
I did not.
What's worse is that
I
you
chose this
made
class,
this.
but not the students. You guys were just a random sampling.
Yeah, it was a little.
We're the best with honors.
Well, you beat one team at least.
You suggested
So,
you take this class.
How are we going to, I did, it's a good
So that's
class.
your fault.
How are we going to integrate this motion, right? Because we've got all these little bits of motion, how are we going to do that? Well, there are a couple things. One is we look at planar surfaces, right? So flat surfaces, okay? So if we see like a flat surface, sort of it's all going to move together, right? So if you're moving your head around, you're looking at this room, you notice the walls, hopefully they all move together coherently. If not, I have to remind you to get under your desks, right? Because that's an earthquake situation. Rigid three-dimensional objects, we'll take a look at that, right? We actually, there's some cool things that happen, right? We really try to pluck out three-dimensional objects when we look at something that's 2D, right? This is why, as Josh told us a couple weeks ago, depth perception, and even in 2D media, why we can fool you, right? Into thinking that things are three-dimensional. How many of you have seen like the chalk art, right? Where the folks will do, like on the sideway, and you'll think, well, that's definitely a hole, but it's not. And then when you get up to it, you're like, yeah, that's not a hole at all. That looks weird. But from a distance, right? Because we're always kind of looking for these things.
Would that be the same with like pointillism?
Pointillism's a little different. That's relying on your inner receptor angle, right? Because remember we said your receptors aren't packed infinitely tight, right? There's some space. And once you get far enough away, there's going to be enough spread of those points that it's all going to blend together.
Gotcha.
The other thing is what we call articulated biological forms. How many of you have ever seen a biological form move?
Yeah.
Yeah, everybody has, right? But there are predictable ways in which that biological form can move, right? All right, so here we go. Here is planar surfaces. Now, there's this very complicated thing called the velocity space model. This is terribly important, but terribly complicated. So what we're going to do is we're going to walk right down the middle of it, right? And I'm going to tell you just what you need to know for it to make sense to you so you'll sleep tonight. Because if I tell you just this much more, you're going to be like, one eye is going to be like twitching open all the time, trying to figure this out, okay? Here's the deal. Things that are coherent objects, they move together. They might move in different directions though, right? And you're sampling, again, Chandler, you're sampling from each of these little places, right? You're sampling the motion in each of those locations. And that's what's represented by these cells here. The problem is if I show you those 4 cells and I say, okay, which way is this object moving? You have no idea, right? Because some of them looks like the edge is moving up, sometimes the edge is moving down, they're moving at different angles, and you think, well, this cannot be a coherent object, right? So we have to take all of those cells and feed those forward into that guy called MT. And your middle temporal area does some fancy calculations, right? And it says, well, assuming all of these locations are on the same object, and they're each moving at this rate and at this angle, how can I calculate the only possible solution to that, right? Basically, it's trying to find the common denominator of direction that would work for all of those angles and that amount of movement. Does that make sense?
One more time.
Really? Because I worked hard on that.
I'm sorry.
So, you've got an object, and you're sampling from, let's say, 4 locations on that object, right? And because it's a weird shape, even though it's all moving together, each of those edges is going to be moving in a slightly different direction according to that small aperture, right?
Okay.
Because you're only getting that, like on that breathing square, you're only getting that small little picture. But if I take those 4 little pictures and I put them together, I've got a brain region that's going to figure out, well, based on these 4 parameters, what is the only way that that entire object could be moving together? Does that make sense? And that's what happens in the velocity space model.
So, are there also cells like the polar cells that were on and off the polar cells? Would something like that play into effect? Like, if something's staying off and not
Absolutely.
detecting light? It's
Yeah,
like that
so
here.
there's a lot of debate, actually, and Chandler, that brings up a really great question. So a long time ago, people said, cortex is the only place where there's any processing, everything else is a relay station. And then some guy came along and he was like, you guys are idiots. Thalamus is doing, that's one step before cortex. Thalamus is doing a whole bunch of processing. Everything before that's a relay. And then there was a guy a few years ago who said, you know what, you're all idiots. There's a lot of processing going on in the retina, right? So there's a lot of stuff going on in the retina before it even gets to the thalamus, which we don't even really understand yet. But you're absolutely right. Those bipolar cells, those amacrine cells, horizontal cells, all of those guys are in different ways, you know, with lateral inhibition and some of those other mechanisms, doing some heavy processing before it even gets back. If you think about how quickly your visual system works and how quickly you can make decisions and send outputs based on that information, it really is pretty obvious that there is a whole lot of processing going on pretty early,
You
right?
want to pull that data as much as possible before it's...
Absolutely, absolutely, right? Because we want that, you know, refined, you know, we want it as refined as possible by the time it gets to these higher areas like MT. All right. Now, this is also going to be part of your lab, right? And unfortunately, you're not going to be able to see it here. But we will demonstrate this in the lab activity. You guys should really think about this while we're doing this, and you should really be appreciative of what Marissa has done, because she almost set this building on fire, trying to prepare this lab activity for us. Because apparently, are these... printing things on transparencies is not something that's easy to do these days. I had assumed it would be something easy, and that's why I'd asked other people to take care of it. Had I been in charge of this, I definitely would have set something on fire. But for these plaids, you have different gratings. How many of you remember the different sine wave and square wave gratings? Yeah, right? What's cool about this is you can overlay these, right? And you can, hopefully, you guys
do a better job.
You're going to have the aperture too, right? So what you would
At least
see,
you're better than someone.
yes.
Yeah.
What you would see is, imagine if this grading is drifting up, and say this grading is drifting over in that direction, right? They're 2 separate gradings. One's going to drift up, and one's going to drift over. What you would in fact see as a according to the velocity space model, and what you guys are going to be able to demonstrate in lab, you would see a plaid that would kind of drift up in an angle, right? Which is sort of this component motion versus global motion, right? So we're looking at the movement of the whole pattern versus the movement of the individual pieces, right? Does that make sense? We'll demonstrate that in the lab. That's a sort of a standard outcome of the velocity space model, is that if you take different gratings and drift them in different directions and overlay those gratings, what you would create is a plaid pattern moving in a completely new direction. Now what's interesting about this is you're going to have some cells that are going to still get really excited about that grading moving up. Some cells are going to get excited about that grading moving, let's say, to the left. And then there's going to be a third set of cells in MT, right, that middle temporal area, that are only going to get excited about that plaid pattern. They're not going to care about those other 2 sort of independent pieces, right? Because they're integrating all of this together. Again, because what are we trying to do, Chandler? Figure out if something's coming directly at us. We're sampling from all of those pieces, putting that together into this nice kind of coherent package. Okay? And here you go. This is just another example where we've taken one component And then a second component, we've added that together, we've created a plaid, because these guys are drifting in different directions. According to the velocity space model, there's only one solution. Okay? Questions about that? I think the lab will help, hopefully, with this. All right, so three-dimensional objects. Let's see if we can get a good demo from this website. I know there's one for biological motion. I thought he had one with a kinematogram. Let's try this trick. Let's see what this is. Okay. So, so if you see this, right, hopefully it appears to be like a three-dimensional kind of tower that you're looking down on, right? What's interesting is it's really, I mean, it's really not, obviously, right? But you, because we live in a three-dimensional world, are going to constantly be trying to pull out three-dimensional information from whatever it is you see, right? Even if it's not really there. Which is kind of exciting. Which is why some of these visual illusions work.
Okay, so you said that we're seeing it that way because we live in a three-dimensional world.
Yeah.
So, like, is that like innate or is that like taught?
Yeah, so that's actually a great question, but it's, so there's a ton of
Cross-cultural, she kind of told us that.
Yeah.
It depends, like, different cultures see things differently. Like, we were looking at different pictures and stuff like that, and she showed us one, like, where there was an elephant
yeah.
behind it, and then, like, in a tree, and the guy with the spear, and, like, everybody in a different culture said, like, why are you trying to kill the tiny elephant? It just depended on, like, because we're taught to see things that are, like, if something's overlapping, then something's in front, you know.
So we'll talk about that in some detail in a couple weeks, right? Because there's like a whole chapter on like individual differences, and we'll briefly talk about culture. I don't want to do too much of a spoiler alert on this. I think the end result is we're really not sure, to be honest with you. Part of the problem is, and this is one of the biggest problems with those particular studies, and they've tried to replicate them, but it's still sort of hard to get around it, is one of the problems with those early studies is they didn't bother to correct for folks who had corrective lenses, right? So that was a problem. Secondly, it's all in how you test people, right? I mean, that really makes a huge difference, right? So if I were to give anyone in this room a drawing of something, you would be able to interpret that in a different way than, let's imagine, someone from a hunter-gatherer society who's not really experienced pencil and paper, right? And so the testing makes a huge difference there. And I think, I don't know, I kind of battle with that one myself, going back and forth, right? Because there has to be a number of things that are innate, right? Because we share this sort of the same, evolutionary history. At the same time, there are obviously things that you can, symbolic. We do have sort of some symbolic representation, and we can learn that. But I don't know. There's this whole thing about the Carpenter world hypothesis, right? And we'll talk about that some too later, and whether or not there's a thing called the oblique effect. Whether or not the oblique effect is more powerful in urban versus, or like westernized cultures versus other cultures. And I feel like the evidence is probably still out on that. Simply because I think testing that is just just a real problem, right? Because how can you, I don't know, it's just hard to like come up to somebody like, I'm trying to think about like how to design this study, and I just have like a giant, all I come up with is like I've got a giant log on like a cranking protractor, and I'm like trying to move it and have people guess what the angle is, right? But that just doesn't really, I don't know, right? Because you can't bring people into a classroom, right? I mean, it just really becomes a problem. We'll talk about it. But yeah, that was a good question. But I think it doesn't matter who you are, what culture you're in. You live in and have evolved in a three-dimensional space, right? And so things are going to be three-dimensional to you. And anytime you see something that is two-dimensional, if you can, you're going to pluck out three-dimensional information from that, right? Simply because everything you see is three-dimensional in the world, right? And so just because something's flat on a sheet of paper, that's been a relatively new sort of innovation, and we're still going to see things in three dimensions.
So is that something for people who don't live in a carpenter world? Like, would that be difficult for them to see? Like, because when we look at things like with the chalk things and stuff like that, it's not actually three-dimensional, just like a tree is actually three-dimensional. So like you see it as three-dimensional, but like if they were to look at the chalk thing, would they see it as three-dimensional like we would? Because we're taught, I guess, to like pick things out and look at them three-dimensional.
I would say they would see it the same, because I think it just relies on basic visual processes, right? Underlying processes that I don't think are going to be different from one person to another, one culture to another. It's going to be the same. Now, what they now you'd have to be, it'd have to be something that they would be familiar with. If you were to make a chalk structure that looked like a hole in the ground, then I think that's going to look the same to everybody, right? There might be some culturally irrelevant things that you might create that they would not, that might not make sense to some people, but that would be, wherever you were. So, but I think it's going to be the same basic process for everybody. I think it's an underlying capability of the human visual system. Feature, I guess I should say. All right. We should also talk about biological motion, right? So we decided most of us have seen things that are moving, that are biological motion, right? Which is exciting. He's got a good biological motion. So I think, and I think this is a good argument against some cultural differences, because I think we can all pick out, we can all kind of say, well, that's definitely looks like a person walking, right? Which I think is kind of interesting. And then this one's one of my favorites.
Looks like he's still
Looks like he's what?
Looks like he's working.
Looks like he's limping, yeah. He does have a little bit of a limp, but it's still clearly somewhat moving, even though it's not in any way relevant information, right? I mean, the information is just like random characters, from the keyboard, and it's not in any way, it's not even all letters. I mean, some of it's like punctuation, but it's still something that appears to everyone to be biological motion. This is kind of an interesting one too. You don't really know what it is, and then you clearly realize that's a guy doing juggling. I don't know if you guys like juggling or not. And I don't think this is going to matter what your cultural background is. You're going to be able to pluck out biological motion, right?
Like that's just human movement, or like?
Just what?
Is that just human, like? Movement,
No,
or just
no, actually it's not. I've seen ones that were like, quadrupeds, things that are moving. You're still going to recognize that as biological motion, right? Which is important because that's a completely different class of things that move, right? If you think about like a tree falling and that kind of visual motion versus a bear running at you trying to eat you, it's a completely different kind of motion. You have to predict what's going on, right? All right. I don't want you to worry too much about this. Just keep in mind there are different ways in which we pull out motion from the visual scene, right? There's this whole debate about feature tracking. This is like a huge debate in vision research. Like, is your visual system capable to pick out a couple key features and track that over some distance or time? There's evidence that says, yeah, that probably happens. There's evidence that says, no, it probably doesn't happen. I think the important thing to take away from this, is we've taken away from other things in this course, is if it's something really important, we probably approach the problem in more than one way, right? So if you remember, sound localization, super important. And what did we have? We had two different mechanisms, right? We had the intraoral time differences and the intraoral level differences, right? So if we're trying to do object recognition, for example, we talked about that, right, Marissa? And we talked about the extrinsic and intrinsic features. There are probably approaches that we use that are more reliant on extrinsic and some that are on intrinsic, right? Because it's such an important thing that we're doing. Visual motion is one of the same things. We're going to use multiple approaches to this, multiple ways that we're going to integrate and try to pluck out that motion. And don't worry about second order motion, or we'll talk about that some other time. Okay, things you'll probably forget.
Not until at least after next Thursday.